is lecture 11 of the metric spaces part of A2, and this lecture corresponds to chapter 5 in the notes. And in this lecture we'll elaborate a little bit on some notions that follow on from the ideas of open and closed that we introduced in the last chapter. So I want to begin by talking about what's called interior and closure. So let's take a metric space X and let S be a subset of X. Then the interior of S is defined to be the union of all open subsets of X that are contained in S. The closure, so the interior is denoted by int of S usually, sometimes by S with a little circle to the top right of it. The closure, which is usually denoted by S bar, is defined to be the intersection of all closed subsets of X which contain S. Now occasionally, we won't see it much more in this course, we also would talk about the boundary of S, which is the closure with the interior removed, so S bar backslash the interior of S. That's sometimes denoted by a kind of partial or boundary symbol of S. And then a final piece of nomenclature is we say that a set S is dense if its closure is all of X. So it's dense in X if its closure is all of X. Now, a couple of preliminary remarks. The interior of S is itself an open set. The reason for that is that it's a union of open sets, and any union of open sets is open, as we saw in a previous lecture. So it's therefore the unique, largest open subset of X that's contained in S. If S is itself open, then S is equal to its own interior, and that's actually an if and only if. Similarly for closures, the closure of S is itself a closed set because an arbitrary intersection of closed sets is closed, and it's the unique smallest closed subset of X containing S. And S is closed if and only if S is equal to its own closure. Let's take a look at a couple of examples. So if S is a closed interval AB, well then its interior, the largest open set contained in it, is just the open interval AB. What about if S is the rationals? Well, then its interior is empty because there's no open set contained in the rationals. Every open interval contains uncountably many irrational numbers. But the closure of the rationals is all of R. And the reason for that is if the closure was not all of R, then there would have to be a proper closed subset of R containing the rationals. But then the complement of that set would be open. But any open subset of the reals contains rational numbers. Every open interval contains rational numbers, so that would be impossible. So the rationals are dense in the reals. So rationals are dense in the reals. And I've remarked also, here's another set, that the rationals with denominator who's a power of 2 are also dense in the reals, for much the same reason. Final example, and this can be the cause of confusion sometimes, it's important to note that the closed ball of radius epsilon, centered on A, is not necessarily the same thing as the closure of the open ball, centered on A, of radius epsilon. So we've seen already that the closed ball is closed, and so therefore the closure of the open ball centered on A with radius of epsilon, well, that's the intersection of all the closed sets containing the open ball. So the closure of the open ball of radius of epsilon is contained in the closed ball of radius epsilon. But the containment can be proper. And so, for example, in fact, if you take X to be any set of at least 2 elements equipped with the discrete metric, then if I take little x to be a point in there, the open unit ball about X, so the open ball of radius 1, is just the singleton point X, and therefore it's closed. And so it's equal to its own closure. But the closed ball of radius 1 is the whole space capital X, as we've seen. So all of this maybe could be a bit confusing. It's very important to distinguish between whether the bar is just above the B, which means the closed ball, that's the set of points at distance less than or equal to epsilon from A, or if I put the bar across the whole of the expression B of A epsilon, that means the closure of the open ball, which is a different thing in general. So something to be cautious about with that. So let's look at some other ways of describing the closure. And here's an important one. Let X be a metric space and take S to be a subset of X. Then I claim that a point A lies in the closure of S if and only if the following is true. Every open ball about A meets S. So that's a nice characterization of the closure. Now let's prove that. Suppose first that A is in the closure of S. Now if I have a ball centered on A that doesn't meet S, well, that's an open ball, so its complement is a closed set and it contains S. And therefore that complement contains the closure of S because it's a closed set containing S, and therefore it contains A because I'm assuming that A lies in the closure of S. But that's obviously nonsense. The complement of the ball centered on A definitely doesn't contain A because the ball centered on A contains A. Conversely, suppose that every ball about A meets S. Then if A is not in the closure of S, well then, because the complement of the closure of S is open, there has to be a ball centered on A that's contained in that set, contained in the complement of the closure of S. But then it's contained in the complement of S, and that's contrary to assumption, because I'm assuming that every ball centered on A meets S. So this is just basic sort of elementary set theory. Is A contained in B? Is the complement of A contained in B, and so on? There's no real sort of analysis or geometry has happened there, just set theory. Now, a particular consequence of this is that a set S is dense, in other words, its closure is everything, if and only if it meets every open set in X. So that follows straightforwardly from the lemma. Let's look at another characterization of the closure. So let X be a metric space, and let's take a subset S of X again, and let A be a point of X. Then the statement is that A lies in the closure S bar if and only if there's a sequence of elements of S, sequence Xn, whose limit is A. So in particular, S is closed if and only if the limit of every convergent sequence of elements of S lies in S. So S is closed if and only if it's closed under taking limits. So let's prove this. Suppose that A lies in the closure of S, and by the previous lemma, every ball of radius 1 over n contains a point of S. This is for an arbitrary natural number n. So for each such n, I can pick an element xn that lies in the ball of radius 1 over n about A, and also in S. But then that is conspicuously a sequence of elements of S whose limit is A. Conversely, suppose I have a sequence of elements of S whose limit is A. If A is not in the closure of S, well then again by the preceding lemma, there's a ball about A that doesn't meet S. But if n's big enough, by the definition of limit, the distance from xn to A would have to be less than epsilon if n is big enough. And for any such xn, well, it then lies in both the ball of radius epsilon about A and in S, and that's a contradiction. So two different characterizations of the closure. Now I want to talk a bit about limit points. So limit points is actually a notion that I personally don't really use very much or happen to think is super important, but it's something that's in the schedule, so I'm going to go over it. But it will only feature in this little section of the course. So if X is a metric space and S is any subset of it, then we say that a point A in X is a limit point of S if any open ball about A contains a point of S other than A itself. And it's this last clause, other than A itself, that distinguishes the notion of limit point from just something that's in the closure of S. This is non-standard, but I'll write L of S for the set of limit points of S. So it's not necessarily the case that every point of S is a limit point of S. So this could happen if there's some ball about point A, so some ball of positive radius epsilon, such that the intersection of that ball with S is just precisely the point A. So if that happens, we say that A is an isolated point of S. So let's just look at that in action. Take the real numbers and let S be the half open interval 0, 1, open on the left and closed on the right, together with the isolated point 2, singleton point 2. Then the set of limit points of S, I claim, is the closed interval 0, 1. Well, let's just briefly remark on why that is. So the point 2 is not a limit point of S because there is an open ball about 2 that only contains the point 2. Whereas by contrast, the point 0 is a limit point of S because every open ball about 0 contains, in fact, infinitely many points of S. So, in particular, we have a limit point that's not in S and a point in S that's not a limit point. So both of those things can happen. Let's prove a couple of statements about limit points. So let S be a subset of a metric space X. Then I claim that the set of limit points of S is a closed subset of X. Okay, so how do we show that something is closed? Well, we show that its complement is open. So suppose that A is in the complement of the set of limit points. Then what that means is that there's a ball about A whose intersection with S is either empty or just the singleton A. So that's the definition of what it means to not be a limit point. And I claim that in this case, the ball of radius epsilon over 2 centered on A is also contained in the complement of the set of limit points. So that will be enough to show that the complement of the set of limit points is open. So let's take a point B in that ball of radius epsilon over 2. Now there are a couple of possibilities. Either B is equal to A, but then we already know that B lies in the complement of the set of limit points because it's equal to A. Or B is not equal to A. Now if B is not equal to A, then I can put some tiny ball about B, which is still contained in the ball about A of radius epsilon, and also misses A. So to do that, I choose the radius delta of that ball. I just make sure that it's less than the distance between A and B to make sure that that little ball doesn't contain A. And I also make sure that delta is less than epsilon over 2, which by the triangle inequality ensures that this ball of radius delta sits fully inside the ball of radius epsilon centered on A. So this ball meets S in the empty set. And therefore B is in the complement of the set of limit points in this case as well. So I've shown that the whole of this ball of radius epsilon over 2 about A is contained in the complement of L of S. So that establishes that it's open and therefore that the set of limit points is closed. Let's have a look at the link between a couple of the notions we've discussed, the notion of closure and the notion of limit point. So again, let S be a subset of a metric space X. Let L of S be its set of limit points and denote by S bar its closure as usual. Then I claim that the closure is, so S bar is S union the set of limit points of S. Now, of course, this might not be a disjoint union. They definitely could overlap. So we'll show two different inclusions. We'll first show that S contained with it, S union the limit points of S is contained in the closure of S. Well, evidently S is contained in the closure of S. So all we need to do is show that the limit points of S are contained in the closure of S. So suppose that A is something that's not in the closure of S. Suppose A is in the complement of the closure of S. Now the closure of S is closed, so its complement is open, and therefore there's a little ball of radius epsilon about A, which lies entirely in the complement of the closure of S. And so it certainly lies in the complement of S, and so we've found a ball about A which doesn't meet S, and that means that A could not have been a limit point of S. So that establishes one inclusion. And now we'll show the reverse inclusion. We'll show that the closure of S is contained in S together with the set of limit points of S. So let's take a point A in the closure of S. Then by one of the characterizations of closure that I gave earlier in this lecture, there's a sequence xn of elements of S whose limit is A. So xn tends to A. Now it might be the case that one of those xn's is equal to A for some value of n. And then we're done, because in that case, A lies in S. So this particular value of A lies in S. Otherwise, well then, none of the xn's are equal to A. Now let's take an epsilon bigger than 0. Then provided n is sufficiently big, all of those xn's first of all lie in the ball of radius epsilon about A, and that's because xn tends to A. But none of them are equal to A. And they all lie in S. So in particular, one of them lies in S, well, infinitely many of them lie in S, intersected with the ball of radius epsilon about A, but minus the point A. So in other words, the ball of radius epsilon about A intersects S in a point that's not A. And that's exactly what it means to be a limit point of S. So that concludes the proof of the proposition. So the final thing to say on this topic is a corollary of that proposition. And this is another characterization of what it means to be a closed set. So let S be a subset of a metric space X. Then I claim that S is closed if and only if it contains all of its limit points. And here's the proof. So I've already remarked right at the start of the lecture that S is closed if and only if it's equal to its own closure. And I've just this minute shown that the closure of S is equal to S to get union the set of limit points of S. So if I put those two things together, I get that S is closed if and only if S is equal to S union the limit points of S. And that's equivalent to the limit points of S being contained in S. Okay, so that's the end of the lecture. I think this is actually somewhat difficult material once you put it all together, but there were very, very few places in this where we used anything more than what I call just basic set theory. So De Morgan's laws, the complement of A and so on. The only point where we really used a little bit of geometry was in the proof of this lemma here about the set of limit points being a closed subset of X. So we use the triangle inequality in the final part of this proof. So let me just remark again that I'm not a big fan personally of this idea of limit points. I find it a little bit confusing. So I've covered it because I'm supposed to, but I won't be using it again in the rest of the course. I think the idea of closure is much more fundamental, so is the idea of being dense, and I will feel free to talk about those later on in the course. This is lecture 12 of A2 metric spaces, and this is the first lecture corresponding to chapter 6 of the notes. And in this lecture, we'll start looking at some properties that may or may not be enjoyed by sequences in metric spaces. So let's have a little look at sequences in metric spaces and some of the properties that they may or may not have. So let X be a metric space and let little xn be a sequence of elements in that space. And here are three possible properties that this sequence may have. It could be bounded, and what that means is that the set consisting of all of the xn's is contained within some fixed finite ball of radius capital R. So all elements of the sequence lie inside some fixed ball. It could be a Cauchy sequence, and that means the following. Informally, it means that as n gets larger, the xn become arbitrarily close together. But more precisely, it means the following. For every epsilon greater than 0, there is a capital N such that if little n and little m are greater than or equal to capital N, then the distance between xn and xm is less than epsilon. So just to clarify, this notion of Cauchy sequence generalizes in the most obvious way the notion of Cauchy sequence of real numbers that you saw in prelims. And when the metric space X is the real numbers, the two notions are the same. And finally, a sequence could be convergent, and what that means is that it tends to a limit, which I'll call A. So the limit of the xn's is equal to A. So here are three different properties that a sequence may or may not have. It may have none of these properties. What's the relation between those properties? Well, let's start by giving some examples where there is no relation. So take X to be the half open interval 0, 1. So it's open on the left and closed on the right. And then look at the sequence xn equals 1 over n. So that's a Cauchy sequence because if n and m are really big, then the distance between 1 over n and 1 over m is less than epsilon. But it's not convergent. And the easiest way to see that is to think in the whole real line R. So in the real line R, that sequence is convergent to 0. But limits are unique, and so it can't also converge to an element that's in X. Now this space X also has a sequence that's bounded but not Cauchy. For instance, the sequence that alternates between 1 and a half. So that's clearly, every sequence in this space X is bounded, but that particular sequence is not Cauchy. So you can be bounded but not Cauchy, and you can be Cauchy but not convergent. So what about other implications? What about the other directions? So it turns out that, in fact, if you're a convergent sequence, then you are Cauchy, and if you're a Cauchy sequence, then you're bounded. So let's prove that. So suppose first that I have a convergent sequence, xn. So the limit as n tends to infinity of xn equals a. So just write down the definition of what it means to tend to a limit, but let's just replace the epsilon there with epsilon over 2. So there's some capital N, such that if little n is greater than or equal to capital N, the distance from xn to a is less than epsilon over 2. Now suppose that I've got two indices m and n greater than or equal to capital N. Then by the triangle inequality, the distance between xm and xn can be bounded above by the distance from xn to a plus the distance from xm to a, and that's at most epsilon over 2 plus epsilon over 2, which is epsilon. So I've shown that it's a Cauchy sequence. Now suppose I have a Cauchy sequence and I want to show that this sequence is bounded. Well, apply the definition of Cauchy with epsilon equals 1. So this tells you that beyond some point, so if m and n are greater than or equal to big N, then the distance between xm and xn is at less than 1. Well, that already tells you that all elements of the sequence from some point on, so x sub capital N and subsequent points, they all lie in a ball of radius 1, the one centered on x sub capital N. And then if I enlarge that ball sufficiently, I can include all the other points as well. So in fact, all points of the sequence lie in the ball of radius capital R about x sub n, where capital R is the largest value in the set consisting of 1 and the distance between xn and x1, distance between xn and x2, and so on, up to distance between xn and xn minus 1. So I can find a specified some fixed open ball which contains all elements of this Cauchy sequence. And so what I have is a bounded sequence. Now we come to a very important definition in the theory of metric spaces, which is the notion of completeness. So remember, we've just showed that every convergent sequence is Cauchy, but we gave an example before to show that the converse is not true. So you can be Cauchy, but not convergent. But in some spaces, there is no such counterexample. So in some spaces, every Cauchy sequence is convergent. And those spaces are the ones that we call complete metric spaces. So a metric space is said to be complete if every Cauchy sequence converges. So in prelims, you saw that the real numbers are a complete metric space. So every Cauchy sequence of real numbers converges to a real number. And we saw just a couple of minutes ago that half open 0, 1 is not complete because the sequence 1 over n is a Cauchy sequence which does not converge. And nor for that matter is the open interval 0, 1 for exactly the same reason. Now, why have I said that? Well, earlier on, we showed that open 0, 1 is homeomorphic to the whole real line. So what we've got here is a non-complete space, open 0, 1, being homeomorphic to a complete space, namely R. And what this means is that the notion of completeness is not a homeomorphism invariant. So this is not what we call a topological property. It very much depends on the particular metric that one's looking at. So the notion of completeness is not necessarily preserved under homeomorphisms. Final piece of nomenclature, if we have a normed space V, then as we've discussed several times, that's also a metric space, and the metric being given by the distance between V and W being the norm of V minus W. Now, that's a metric space. We can ask whether or not it's complete, and if it is, then we say that the normed space is complete. So when we talk about a complete normed space, what we mean is a normed space such that when thought of as a metric space, with the metric induced from the norm, it's a complete metric space. Let's start to prove some basic results about complete metric spaces. And the first thing to look at is the situation where you've got a subspace of a metric space, subspace of a complete metric space, and you want to know whether that subspace is complete. And here is the basic theorem about that situation. If you've got a complete metric space, a subspace of it is complete if and only if it's closed. So let's give the proof. Now recall that if you've got a set Y in a metric space X, then Y is closed in X if and only if the limit of every convergent sequence little y sub n of elements of Y lies in Y. So we showed that in previous lecture, characterization of what it means to be closed. So suppose now that X is a complete metric space and that Y is a subset of X. And we've got two directions to consider. So first we'll look at the if direction. So suppose that Y is closed. We want to show that Y is complete. So take a Cauchy sequence in Y consisting of elements little yn. Now that's also a Cauchy sequence in X because the distances on Y and X are the same, at least for elements of Y. Now X is complete and we've got a Cauchy sequence and so it converges. So it converges to some point A. But Y is closed and so that limit must in fact be in Y. So our Cauchy sequence of elements of Y converges to an element of Y and so Y is complete as a metric space. The only if direction, well, suppose that Y is complete and suppose we have a sequence little yn of elements of Y which tend to A. Then what I want to show is that A lies in Y. Well, this sequence yn is convergent and so it's Cauchy, as we showed at the beginning of the lecture. And by the assumption that Y is complete, it converges to an element of Y. So we've shown that we know that it converges to A and also to an element of Y, and therefore A must lie in Y. So the limit must be in Y. So this means that Y has to be closed. Let's move on to another theorem maybe not such a basic theorem, but an interesting theorem about complete metric spaces. And this is called Cantor's intersection theorem. And here's what it states. It's a very natural sort of statement. Let X be a complete metric space, and suppose I have a nested sequence, S1 contains S2, contains and so on, of subsets of X, and that they're all closed and they're all non-empty. Moreover, their diameters, so that is to say, the maximum, the supremum of the distances between elements in those sets, tends to 0 as n tends to infinity. Then the conclusion is that they have a unique point in their intersection. So think of these sets as sort of, think of a diagram of nested circles, if you like, and they zero in on a unique point, A. So let's prove that. Well, for each n, we'll pick a point in Sn. Pick a point xn in Sn. And I claim that that sequence is automatically Cauchy. Well, let's prove that. Let epsilon be greater than 0, and I will choose capital N's sufficiently large that the diameter of S sub capital N is less than epsilon. Now, if little n and little m are bigger than this capital N, then because of the nesting property of these SIs, then the corresponding elements x little n and x little m must both lie in S big N. So x little n lies in S little n, but S little n is contained in S big N. So those two elements both lie in S sub big N, and therefore by the definition of diameter and the fact that the diameter of S sub big N is less than epsilon, the distance between x little n and x little m is less than epsilon. So what I've got is a Cauchy sequence. I've proven that now. X is assumed to be complete, and therefore this Cauchy sequence has a limit, which I'll call A. Now, if n is greater than or equal to I, well, by the choice of, so here n and I are just two positive integers. So by the choice of the xn, so xn lies in Sn, and Sn is contained in Si by the nesting property. So in other words, for all n greater than or equal to I, all of those xn's lie in Si. So think of I as fixed and n tending off towards infinity. But Si is a closed set, and therefore, if I've got a convergent sequence of elements of that set, then its limit also lies in the set. So the limit of the xn's, that is to say A, lies in Si. Now I was arbitrary, and so A lies in the intersection of the SIs. So I've shown that this intersection does contain a point. Now I need to show that it's unique. So suppose that B is another point in this intersection. Well then, the distance between A and B, so A and B, for every I, they both lie in Si, so the distance between them is less than or equal to the diameter of Si. So if you just let I tend to infinity, because the diameter tends to 0 as I tends to infinity, this forces you to conclude that the distance between A and B is in fact 0, therefore A equals B. So that's Cantor's intersection theorem. Well, maybe it's slightly interesting to ask what happens if we drop some of the conditions there. What if we drop the condition that the diameter of the SIs tends to 0? Well, we certainly wouldn't expect the intersection to be unique, because, for example, we could take all of these sets Si, so there's a small misprint there, we could take all of these sets Si to be the whole space X. Somewhat surprisingly, at first sight, if we drop that condition that the diameters of the Si tend to 0, then the intersection could even be empty. And actually, once somebody tells you this, there's a fairly obvious example. I could take Si to be the real numbers greater than or equal to I. So those are all closed sets, they're nested, and they sit in a complete metric space, but there's nothing in their intersection. Okay, so that's the end of the core part of the lecture. I just want to make a remark for enthusiasts, yes. So at this point in the proof of Cantor's intersection theorem, I have used something called the axiom of countable choice. And I don't really want to digress too lengthily on this now, but I just want to make you aware of the fact that I've used an axiom of set theory that is not one of the most basic axioms, and in a certain sense, historically at least, has had some controversy around it. So the fact that it's possible to pick an element of a sequence of sets like this. So if I've got a sequence of sets Sn, the fact that I can form a sequence little xn by picking one element from each one, the fact that it's possible to do that is independent of other basic axioms of set theory. So this is called the axiom of countable choice. There's a bigger version of it called the axiom of choice, and this is something that you'll talk a lot more about in the set theory course in part B. But I just want to make you aware of the fact that here I've touched upon some set theoretic issues. Okay, so that's the end of lecture 12.